Okay, so kinetic molecular theory says that the components of a gas mixture act independently. So up till now, we've been assuming that it's just a pure gas, one kind of particle. What if you have two different gases in there? The size of the gas particles don't matter under ideal conditions, and they don't interact with each other. So it really doesn't matter what the components are. They act like they're the only gas in the container. So the gas exerts a pressure. Let's say we have gas A and gas B. Gas A thinks it's the only gas in there. It exerts a pressure. Gas B thinks it's the only gas in there. It exerts its own pressure. The total pressure of the gas is the sum of those pressures. The pressure of each individual gas is the partial pressure. It's not the total pressure, it's the partial pressure. If gas A is half the mixture, then the pressure, the partial pressure from gas A is half the total pressure. If it's 1/4 of the gas composition, then the pressure is 1/4. So the partial pressure exerted by a gas is equal to its fractional composition. Is it 0.5? Is it 0.25? Is it 0.9 out of the total times the total pressure? So the air in our atmosphere is mostly nitrogen, 78% nitrogen, 21% oxygen, 0.9% argon, 0.04%, give or take, carbon dioxide, and some other gases in smaller amounts. You don't need to remember that. So there are different gases in the air that we're breathing. They each exert a pressure. So what's the pressure of the atmosphere? 1 atmosphere. Okay, 1 atmosphere. So if the nitrogen is 78% of the air, it exerts 78% of the pressure. 78% of 1 atmosphere is 0.78 atmospheres. Oxygen molecules exert a pressure, 21% of the total pressure, because they are 21% of the mixture. So there's the optimist who says the glass is half full. There's the pessimist that says the glass is half empty. And then there's the chemist that says the glass is 50% water in a liquid state, 39% nitrogen, 10.8% oxygen, 0.44% argon, and 0.06% carbon dioxide. No comment. Fractional composition, where's my pointer? There it is. Fractional composition is the percent divided by 100. So in this gas mixture here, 80% helium, 20% neon. The total pressure is 1 atmosphere. If we wanted to calculate the partial pressure due to the helium, we take the percentage of helium and convert it to a fraction, dividing by 100. So 0.80 times the total pressure. The total pressure is 1 atmosphere. And so the pressure from the helium is 0.80 atmospheres. The pressure from the neon is 20%. Convert 20% to the fraction, dividing by 100, so 0.20 times the total pressure. 20% of the pressure is from the neon, 0.20 atmospheres. If you add those up, they add up to the total pressure. Any questions? This is the same math that you would use if you're trying to find the percent, if you're trying to find the amount of money that you're going to save by buying the dress when it's 40% off or something. It's the same math. It just seems confusing because we're talking about partial pressures and gases. So a gas mixture contains 64% methane, 36% ethane. If the total pressure is 1.44 atmospheres, what are the partial pressures? Well, the partial pressure of ethane is going to equal its fractional composition. So I started with ethane, I don't know why. Alphabet, that's why. 36% ethane. How do I convert that to a fraction? Divide by 100, so I get 0.36. So 0.36 times the total pressure. So that's 0.36 of the total pressure. It's 36% of the total pressure, right? So 0.36 times the total pressure, 1.44 atmospheres. So 0.36 times 1.44. My calculator gives me 4 digits here, and the unit would be atmospheres. How many significant figures should that result have? 2. 0.36, 36% is just 2 significant figures. It's not exact because it's a whole number. So I would say that's 0.52 atmospheres for the ethane. For the methane, the partial pressure of the methane, 64% of the gas is methane. I convert that to a fraction by dividing by 100. So 64%, 0.64 times the total pressure, 1.44 atmospheres. I'm finding what is 64% of 1.44. .9216. That also would have 2 significant figures, which would round to 0.92 atmospheres. Now, if I add these 2 partial pressures together, what should I get? You should get 1.44, the total pressure. And if we add those together, we do. Now, occasionally, you might do a problem like this, and when you add it together, it'll be 1.43 or 1.45. Does that mean you screwed up? No. The last digit is uncertain. Okay, we do calculations, and there's some uncertainty from the original numbers, and so they don't always come out exactly perfect. It's okay. Any questions? So Dalton, you may remember him from Dalton's atomic theory, same Dalton. Dalton's law of partial pressures says that the sum of the partial pressures of each component in a gas mixture will equal the total pressure. So the total pressure of a gas is equal to the pressure exerted by each individual gas. This is similar to saying that if you have a box of fruit and you've got apples and oranges and bananas, the mass of the fruit in the box is equal to the mass of the bananas plus the mass of the apples plus the mass of the oranges. Makes sense, right? Same thing with the pressures of a gas. So this is a problem that might help you with today's pre-lab question. A sample of hydrogen gas is mixed with water vapor, water in the gas state. The mixture has a total pressure of 745 torr, and the water vapor has a partial pressure of 24 torr. What's the partial pressure of the hydrogen gas? So here we have a gas mixture. We've got water and we've got hydrogen. The total pressure of that mixture is equal to the pressure from the hydrogen gas plus the pressure from the water vapor. Okay? We're told that the total pressure is equal to 745 torr. And we're told that the water exerts a pressure of 24 torr. How do we find out the pressure for the hydrogen? We need to subtract, right? So the pressure for the hydrogen is equal to the total pressure minus the pressure for the H2O. So 745 torr minus 24 torr, which should be 721 torr. That makes sense? The math here is so easy that it becomes difficult. Yeah.
Do we need to further convert this to atmosphere?
That's a good question. Do we need to convert this to atmospheres? No. No, we don't. It's important that these two pressures be in the same unit, right? Because you can't subtract apples from oranges. You can't subtract atmospheres from torr. But as long as these are the same unit, it's fine. This question is not asking for a particular unit. If it asked, what's the partial pressure of the hydrogen gas in atmospheres, then we would need to take this and convert it to atmospheres. But otherwise, no. Any other questions? Our lungs perform best at an oxygen partial pressure of 0.21 atmospheres, which happens to be the partial pressure of oxygen at sea level. So, this is a good place to be. We've got the right amount of oxygen. Our lungs can tolerate higher and lower levels, but there are limits. So at higher elevations, the total pressure of the atmosphere is less, and so the partial pressure of oxygen is less. And so when we breathe, we're not getting as much oxygen. Our bodies aren't used to that, and so we feel breathless. We feel like we're out of breath, even though we maybe weren't running or exerting ourselves. You go a little too far with this, and you get hypoxia, oxygen starvation. You may have heard of elevation sickness. You may have experienced this. You got in the mountains, you get a headache, and you just feel really rotten. It's because your body's not getting enough oxygen, and some people are more sensitive to it than others. So air at the surface, 0.21, you go much below that, and you start getting into hypoxia. Your body's not functioning well. So less than 0.1 atmosphere is severe hypoxia, and that can kill you. But like all things, too much is bad for you as well. 100% oxygen at the surface is going to be okay for you at 1 atmosphere of pressure. If you're exerting yourself, 1.4 atmosphere would be okay. At rest, 1.6, but above that, too much oxygen can also kill you. So, we have this negative connotation about chemicals, right? Chemicals are bad. Things that are natural are good, right? Well, arsenic is natural, and that's toxic. Cyanide is natural, that's toxic. Oxygen is natural. Oxygen is necessary for life, but too much will kill you. So it's all about the amount. Oxygen toxicity is above 1.4 atmospheres. This doesn't happen to you if you're just, going about your everyday life, but it can happen if you're scuba diving and breathing pressurized air. You get twitching, tunnel vision, convulsions, and death. Lovely. So pressurized air, because the total pressure is higher, has a higher partial pressure of oxygen. That's why it can be dangerous. It also has a higher pressure of nitrogen, and nitrogen can also be toxic. It's called nitrogen narcosis because it's a little bit like being on narcotics, also described as rapture of the deep. Feels like being a little bit drunk. You might think, well, that's not so bad. Yeah, but if you're several meters, several tens of meters under the water, you don't want to have impaired judgment, right? So when deep sea divers go diving, they use a mixture of gases such as heliox, which is a mixture of helium and oxygen. And so there's no nitrogen in there, so you can avoid the nitrogen narcosis. And by adjusting the mixture that you're breathing, you can also avoid oxygen toxicity. Okay, so all of that's just sort of background stuff. Here's a question. A diver breathing heliox with an oxygen composition of 5% wants to adjust the total pressure so that the oxygen partial pressure is 0.21 atmospheres, which is ideal. What must the total pressure be? So you don't really need to know any of that. You don't need to remember any of that stuff I told you just now. Here we've got partial pressure of oxygen is 0.21 atmospheres. We've got, it's 5% oxygen. So the fraction there, and your book doesn't give you a letter for this, but the fraction, 5% divided by 100 is what? 0.05, not 0.5, 0.050. So the partial pressure of oxygen is equal to 0.050 times the total pressure. We learned that a few slides ago. We know what the partial pressure is. We want to know what the total pressure is. So what we need to do is divide both sides by 0.05. So we can get total pressure by itself. The total pressure is going to be, total pressure will equal the partial pressure divided by the fraction. So 0.21 atmospheres divided by 0.050. 0.21 divided by 0.050, 4.2 atmospheres. Both my numbers had 2 sig figs, so 2 sig figs is good for the answer. Any questions? We often collect gases over water. Gases can be difficult to work with in the lab because they don't stay in the container very well. They'll escape, right? So how do you trap them? Well, this is one method. So here we have a glass container, well, a container, doesn't matter what it's made out of. A container was full of water and we inverted it in this dish of water. And initially what happened was nothing. The water stayed in there because this water is less than 32 feet tall. Here we have our reaction, zinc and hydrochloric acid, and those are going to react and it's going to form hydrogen gas. The hydrogen gas is going to escape through this tube and keep going and keep going and keep going, and it's going to escape here at the end. It's going to bubble and it's going to go up through the water and it's going to get trapped because this container's inverted. It's going to push some of the water out, so it's going to displace the water. So we're trapping the hydrogen gas. This is called collecting over water because we collected it and it's above the water, right? The thing about this is that the water evaporates. And so above the water here in this space, we have the hydrogen gas, but we also have water that evaporated from the liquid. So we have a mixture. We can measure the volume and the temperature and the pressure of this gas, but it's 2 different components. So we need to use Dalton's Law of partial pressure. So let's say we collected gas over water at a total pressure of 758 millimeters of mercury. So the total pressure is 758 millimeters of mercury. The temperature is 25 degrees Celsius. We want to know what's the partial pressure of the hydrogen gas. Well, we have two gases here. We have hydrogen and we have water. The vapor pressure of the water is dependent only on the temperature of the water. So we don't have, this is difficult to measure, but we don't have to measure it every time because people have done it and made tables for us. So we know the water's at 25 degrees Celsius, so we look it up in a chart. If the water's 25 degrees Celsius, then the vapor pressure of water is 23.8 millimeters of mercury. So if we want to know what the partial pressure of the hydrogen is, so pH2, that's going to equal the total pressure minus the partial pressure of the water. So 758 is the total pressure. And the partial pressure of the water at this temperature is 23.8 millimeters of mercury. 758 minus 23.8. 734.2. What about significant figures? It's really tempting to say 3. We're subtracting here. We need to look at decimal places. So this one ends in the ones place. This one ends in the tenths place. This has 1 decimal place. This has none. And so our answer should be rounded to 734 millimeters of mercury. Any questions?